So here is the atmospheric CO2 record taken from ice cores over the last 800,000 years compared to the plot we've already seen, which is the global delta 18O value of seawater, right? So this is the approximation of the volume of ice on Earth through time that's been derived from the oxygen isotope composition of 4am shells. And so now we're comparing it to direct measurements of the CO2 of the atmosphere as it is recorded by ancient air bubbles locked up in ice cores. So CO2, the axis is over here on the right, corresponds to this yellow curve. So this yellow curve you can see going like this is the ice core record of CO2 concentration of Earth's atmosphere over the last 800,000 years. Again, importantly, this is not a climate proxy here. This is a direct measurement of the atmospheric conditions over the last 800,000 years. The red line is shown here as the global sea surface temperature. And so this is another climate proxy. It's going to be one similar to the global ocean oxygen isotope composition. So it's, we're not going to discuss exactly how this proxy was put together, but it's similar to the oxygen isotope record, and it's an estimate of the global sea surface temperature through time. So both the sea surface estimate and the measured CO2 concentration here is compared to the global oxygen isotope of seawater measured from benthic 4ams. Okay, so here on this right-hand side axis, we've got CO2 measured in parts per million by volume. Parts per million by volume. So that's a ratio similar to a percent, right? So a percentage is the ratio of something out of 100, right? And parts per million is the ratio of something divided by 1,000,000 instead of divided by 100. So this is a unit of measurement for very small numbers. So parts per million by volume is a convenient way to talk about the small amounts of something because it is unitless, by which we mean there's no units like liters or pounds or anything like that attached to it, because it's simply a ratio. So parts per million by volume, that tells us that we are talking about volumes here. So if we take any unit of volume that we want, that could be 1 gallon, that could be 1 liter, right? Any unit of volume that we're familiar with, and we divide it up into 1,000,000 pieces. Then what parts per million means is, of that 1,000,000 pieces of 1 gallon or 1 liter, how many of those millions of pieces would be represented by something like CO2? So let's just say 100. Let's just say that we're talking about a concentration of 100 parts per million. Okay, how could we express that as a percentage, right? So we're familiar with percentages. We divide things into pieces of 100 and then figure out of that 100 how much are we talking about. So if we want to turn this into a ratio where 100 is on the bottom, we're just going to have to lose some zeros. So we lose 1, 2, 3, 4 zeros. Move our decimal place 4 over on the top. Great. So we would now have a concentration of 100 parts per million. You could think of that as, another way to think of that is 0.1%, or 0.01%. So it's really just it's a pretty familiar concept. We're just used to doing it in hundreds, but for very, very small concentrations of things, it's useful to talk about parts per million. So back to this plot, we can see that over the last 800,000 years, the concentration of carbon dioxide, CO2, in Earth's atmosphere has varied from 280 to 180 parts per million over the last 800,000 years. And we see that the high points in CO2 concentration, all these high points shown by this yellow curve, they seem to match up very well with estimates of the global sea surface temperature also being relatively high. The global sea surface temperature here is shown as sort of variation around the median value over the last 800,000 years. So this is sort of, 1 degree warmer than the median value, 2 degrees warmer than the median value, and then 1 and 2 degrees colder than the median value. And so what we see is that over the last 800,000 years, when global sea surface temperature is high, then the atmospheric concentration of CO2 is high. Also down here on the ice core proxy, the volume of ice on Earth proxy from benthic forams, we see that when the oxygen isotope composition of the oceans is relatively light, remember we've got negative numbers on our delta values up here showing lighter oxygen in the oceans. That means that we have relatively less ice on the Earth. So these three records are all telling us sort of the same thing. And there's less ice on the Earth. The global sea surface temperature is higher, right? It's warmer, and there's more carbon dioxide in the atmosphere. We would expect the planet to be warmer because carbon dioxide is a greenhouse gas. So these three records are telling us that the temperature of Earth's surface and the volume of ice and the amount of CO2 in the atmosphere have all sort of varied generally in step with each other over the last 800,000 years. So we talked about last week how the volume of ice on Earth through time over the last 800,000 years is likely controlled by changes in Earth's orbital parameters, right? The orbital cycles of obliquity, precession, and eccentricity that change the amount of solar insolation that is hitting the poles, the north and south poles. And so we know that the changes in ice volume are caused by these orbital cycles. And so it seems like the global sea surface temperature and atmospheric CO2 are also varying on the same timescales. So perhaps a crucial question to ask, if we want to think about the importance of CO2 in the atmosphere, is where does this CO2 go when there's a lot of ice on the planet, right? When we're in a glacial period and CO2 drops and gets lower, where does that CO2 go if it's not in the atmosphere? And how does it get back into the atmosphere, right? So that's going to be an important question to try to understand the significance of this greenhouse gas, CO2. So to figure out where the CO2 goes during glacial periods, right, when the Earth's relatively cold, we're going to have to go back and think about the carbon cycle. So we talked about the different major reservoirs on Earth, and the most important one for figuring out where the CO2 goes during the glacial periods is going to be understanding the deep ocean. So if you recall, the surface ocean, right, the shallow parts of the ocean are very well mixed by wind and wave action, and so they're constantly exchanging atmospheric O2, oxygen, and CO2, carbon dioxide, sort of in equilibrium, constantly exchanging these gases with the atmosphere. And then in the deep ocean, we know that some oxygen makes it down to help decompose dead critters at the bottom of the seafloor. But to sort of understand this process in a little bit more detail, we're going to need a new diagram and to think about this on a different sort of scale. Okay, so here is sort of a schematic cross-section through the Atlantic Ocean from the North Pole, where Greenland is, down to near the South Pole, where Antarctica is. So you can sort of imagine just taking a sort of straight line right down the middle of the Atlantic, going from Greenland down to Antarctica. Okay, so to understand where CO2 is going to go during glacial periods, we're going to have to think about how oceans, or how water circulates in the deep oceans. So we know that in the shallow oceans, the ocean water is constantly exchanging oxygen and CO2 with the atmosphere, but eventually that shallow water needs to get taken down into the deep part of the ocean. And so that happens in the Atlantic Ocean. That happens in the North Atlantic off the coast of Greenland. The water is very cold and very salty up in this part of the ocean, and so that causes it to sink. So we know that hot air rises and cold air sinks. Hot water and cold water do the same thing. So cold water is going to sink in the northern Atlantic down into the ocean. And we call this deep water formation. Now, cold water sinking in the North Atlantic brings down CO2 and oxygen with it. And the reason that it does this is because cold water is able to hold more dissolved gas inside of it than warm water is. So when this water sinks, it's very CO2 rich and very O2 rich. So there's a word to describe this phenomenon, and it's called solubility. So the solubility of gases, including CO2 and O2, increases in colder water. So that means that the gases, CO2 and O2, can be dissolved in, oh hey Leo, there's Leo the cat, dissolved in cold water more easily than they can be in warm water. So we already have some experience in this class with the idea of gases being dissolved in fluids. So we talked about how gases are dissolved inside of magmas, and when they come out of solution and form bubbles, that can cause explosive eruptions, right? So we know that these gases, they're not present as bubbles in the water, right? Fish don't swim around and gobble up air bubbles. They pull dissolved oxygen out of the water with their gills. And similarly, our carbonated beverages, they have CO2 gas dissolved into them that then forms bubbles when we open the cans and break the seal, and those bubbles then come out of solution. So we already know that gases can be dissolved into liquids, and so cold ocean water that's sinking near Greenland is bringing a lot of dissolved CO2 and oxygen down with it, because the solubility of gases increases in cold water. And solubility is the measure of how able a substance is to be dissolved into a solvent or into some other substance. So solubility is how easily a gas can be dissolved in another substance. Okay, so if colder waters can hold more CO2, then, and we know that the global oceans get a little bit colder during glacial periods, is this change in the temperature of the oceans enough to account for all the missing CO2? The short answer is no, that the drop in temperature of the world's oceans, which is estimated by this climate proxy here, right? This red line, this is the temperature of the world's oceans, the global sea surface temperature. So so we know that it gets colder during glacial periods. Is this decrease in ocean temperature enough to tuck away all this CO2 just because the solubility of CO2 increases in cold water? The answer is no, that this actually only accounts for a very small percentage of CO2 storage. So we need some other process to draw down CO2 quite as dramatically as happens in between these glacial and interglacial cycles. I just want to note real quickly that the change in CO2 concentration between glacial and interglacial cycles is about 100 parts per million, between about 180 and 280 parts per million by volume. So meanwhile, remember that we've got these photosynthetic critters that live in the surface of the ocean, things like phytoplankton, and so they're pulling CO2 out of the atmosphere through photosynthesis, and they're converting it into organic carbon, right, turning that into their bodies, and then they die and sink to the bottom of the ocean. Right, and so all this dead organic carbon piles up on the bottom of the ocean floor. Then the cold CO2 and O2 rich deep water kind of comes flowing down along the bottom of the ocean. And remember, it's rich in not only CO2 but also in O2, and so that O2 is going to oxidize this dead organic matter, help it decay, and in that process, more CO2 is released into the deep ocean. Okay, so the oxidation of this dead organic matter releases even more CO2 into this deep water. So now this deep water is like really charged with O2, with CO2. It's got the CO2 that it's carried down from the surface just by exchanging with the shallow ocean, and then it's been supercharged with the CO2 that's released by the decay of dead organic matter. So now this deep ocean water is supercharged with CO2. Okay, so now we've got this supercharged, really CO2-rich deep ocean water. But so how does this deep ocean water get back up to the surface to, exchange more CO2 with the atmosphere? So to that, let's turn to another figure. So here again, we've got a view of the southern hemisphere, sort of from the bottom of the planet looking up. So here in the middle is Antarctica, and we can see these blue arrows are showing this very strong circular wind pattern that kind of blows all the way around Antarctica. This is one of the sort of global scale wind patterns that's caused by like those convection cells that we talked about in the very beginning of this section, and so it causes this very strong wind pattern to sort of just blow this giant circle around Antarctica. And that's significant because the stress of the wind, the sort of friction of the wind on the surface of the ocean, causes the water at the surface of the ocean to move. Right. So here we can sort of imagine this is like the coast. Imagine this is sort of the coast of Antarctica, maybe here. And so we've got some wind blowing towards us, which would be sort of in the same direction as shown in this figure here. But remember, in the southern hemisphere, the Coriolis effect sort of causes this deflection of the way things move, right? So it's sort of a deflection to the left in the southern hemisphere. And so basically what this means is that the strong surface winds cause ocean water to move away from the coast of Antarctica, and that causes what's called upwelling, where deeper water sort of rises up to take the place of the surface water that's being blown offshore. So what that means is that because of these very strong winds surrounding Antarctica, there's also a very strong upwelling of really, really deep ocean water rising back up to the surface to fill in the space that's left behind when this ocean water near the surface is sort of blown out of the way, away from the coast. So back to this diagram, we need to imagine strong winds sort of blowing in this direction, like into the page, right? Sort of going into the page in this direction. And so to show that, I'm gonna draw like a little circle arrow pattern here, and just know that this represents wind that's blowing in that direction into the page. And so that's the very strong wind pattern that goes all the way around Antarctica. And it causes upwelling of deep ocean water to come back up to the surface. Now, once it reaches the surface, particularly the very shallow upper ocean, then some of the CO2 that was released from the decay of organic matter is released back into the atmosphere. And remember from last week when we talked about the carbon cycle that this is, this process is generally in balance. Okay, so how does this process explain, where CO2 goes during glacial periods? Well, during glacial periods, this wind pattern that is, whipping around Antarctica gets moved further to the north. And so let's look at what that means back on this map here. So if this wind pattern that's circling Antarctica sort of gets pushed a little bit further to the north, sort of in all directions, now you'll notice that there are a few continental masses sort of in the way of these winds. One of the reasons that this wind current is so strong is because there's nothing but open ocean surrounding Antarctica, and so they have nothing to, no topography to kind of, stop their progress. These winds can just whip right around. But if they get pushed a little bit further north, all of a sudden they sort of have to cross the southern end of South America, little bits of South Africa and Australia, right? So even a small nudge of this wind pattern further north in all directions actually serves to sort of decrease the strength of this wind pattern. And so that decrease in the strength of the wind is going to decrease the amount of upwelling that happens along the edge of Antarctica. Okay, so when this circumantarctic wind that we've shown with this sort of curved symbol here, remember that's going into the page, gets pushed further north, it has other land masses it has to cross, and so the strength of that wind is decreased, and the strength of upwelling sort of gets decreased. So upwelling is less efficient in the ocean. Things kind of don't, come all the way up to exchange with the surface water. So that means that rather than coming all the way back up to the surface, some of this water doesn't quite make it, and all of this CO2 that was, released by the decaying organic matter at the bottom of the sea ends up staying in the deep ocean for a much longer time. So less CO2 is returned to the atmosphere, more CO2 ends up being stored in the deep ocean during glacial periods. So that's what happens. That's what happens when global CO2 of the atmosphere is drawn down when Earth gets colder during those glacial periods. More CO2 is trapped in the deep ocean through this process. And this is a combination of two processes that are referred to as the solubility pump, which refers to cold ocean water being able to pull more CO2 down into the deep ocean whenever it's colder, and also the biological pump, which is the constant transport of organic matter, dead organic matter, down to the seafloor, where it's decays and turns into CO2. So these two things are called the solubility and biological pumps, and they control the storage of CO2 in the deep ocean on these glacial interglacial timescales.